That's what so yes. So let us start. I'm pleased to introduce our colleague, Professor Eugene Krasovskii. Eugene graduated Moscow Institute of Physics and Technology, known as FISTE, in 1984, and received his PhD 3 years later in 1897 from Ukrainian Academy of Science. And since 1997, he worked in Germany, where he habilitated in 2001. And since 2009, he is Eckerbask Research Professor. His area of interest in condensed matter theory includes ab initio theories of low energy electron diffraction, angle, spin, and now time-resolved photoemission, and surface science. Eugene has developed his own code based on original implementation of linear augmented plane wave method of electronic structure calculation, and this code has several unique features. For example, it can compute asymptote Wigner Smith delay time for electronic states in the energy interval up to several hundred electron volt above Fermi surface. Very technically complicated task. So let us.
Thank you very much, Roman, for the introduction. And because this is supposed to be a very general lecture, let me start with saying a little bit more words about my area. So I'm an ab initio scientist, and people of my profession are united in this so-called Psyche network, where developers of the computer codes and the users exchange their packages. And this is quite a wide area. So nowadays, like one usually thinks of an ab initio scientist as someone who has enough education to download a computer package from the internet and use it to produce some material-dependent parameters for the clever models developed by real physicists. And that's actually not what I mean when I say an ab initio scientist. In my definition, it is someone who believes that solids are made of atoms. And so what we are trying to do is to derive the Hamiltonian from the atomic structure of the realistic solid and solve the equations that arise. And this sometimes leads to mutual misunderstanding with more traditional model scientists. And let me give you a couple of simple examples. For example, there is a very simple and transparent to the Linhart model for the dielectric function. There is only one parameter, the Fermi radius. So let's calculate the Fermi radius for a electron-like metal like aluminum. And when we calculate it, okay, so what's that? Where do we see here the Fermi radius? Or it is well known that at high energies, the band structure is plane wave-like. So we can describe everything with the effective mass. So please calculate the effective mass. And you get something like that. So the effective mass is here. Or a very popular recently, the Rashba, also very transparent, the model for the splitting of the surface states. So please calculate me a Rashba parameter. Then you take a system for which the Rashba model is supposed to work, and you get that from the microscopic calculation. So where the Rashba parameter is here. So what I would like to say with that is that ab initio calculations as such may be not very helpful in combination with simple models. And at least when one takes them seriously, and one has to be very careful. But there are cases when ab initio calculations may be valuable in themselves, because they can produce some scientific information which is not contained in any of the models derived from the physical intuition. And I will be talking about an example of one such study, and it refers to time-resolved photoemission, time-resolved spectroscopy, in particular, the temporal aspects of electron scattering. So let me introduce first my collaborators. In the first place, our chairman and other people closely connected to the IPC or frequent visitors. And basically what I would like to talk about is I will introduce the Wigner delay formalism for scattering, then explain how the temporal parameters, the times can be measured experimentally, and how this can be addressed from the ab initio point of view. And then we shall consider the specific example of electron transmission and reflection from graphene. Okay, so everything starts with a simple problem, which I first encountered some 50 years ago. So two balls move along two different potential reliefs. And the question is, which one comes earlier? Which one comes first? So in classical mechanics, we solve the problem by knowing with which velocity the ball moves at each small part of the trajectory. And then we sum up the times one needs to traverse each of the small spatial intervals. Of course, we cannot do that in quantum mechanics because the position of the particle is not well defined. And apart from that, there are phenomena like tunneling. So it is not clear how to, it is not possible to define the velocity when the particle has negative energy when it tunnels. The velocity operator, the operator is well defined, but we cannot ascribe velocity to it. So this method is not applicable. So there is no analogy with the classical mechanics here. And this was first addressed, and the question of the transmission time in tunneling was first addressed in 1932 by McCall, who performed a quantum mechanical calculation and concluded that basically there is no time needed to traverse a barrier. But his calculations were not very transparent because it allowed for very different understanding on what it means to transfer to traverse the barrier. So it did not have a big resonance, but in 1955 and around this time, Wigner suggested formalism to address the timing of scattering. So he noticed that the equation of motion of a particle before scattering is the same as after the scattering, because in the unperturbed region, the Hamiltonian is the same and it is free motion. And the two equations of motion differ only by a shift, which can be calculated as the energy derivative of the scattering phase. So in the asymptotic regions to the left and to the right from the scattering, the wave function has the same shape, so it differs only by a phase. And the energy derivative of this phase just gives us the shift of the equation of motion. In 1962, this formalism was applied to tunneling by Hartmann, who obtained a rather counterintuitive result that the traversal time for a barrier does not depend upon the width of the barrier, which means that if we ascribe a velocity to the motion under the barrier, then this velocity is unlimited, and consequently it may be larger than the speed of light. And this observation has never been doubted, but it gave rise to hundreds of theoretical papers that tried to reconcile this with the special theory of relativity and understand why actually this is true. And also the experimentalists immediately found such examples and claimed several times that the superluminal behavior was observed for photons and for atoms, etc., etc. The theoretical discussion keeps going, so the papers keep being published. But I think in 1996, the situation was already summarized by Professor Haag, who in his brief review can one speak about tunneling times in a polite society? Answered this question, no, one cannot. But still, like, we can measure the temporal characteristics of scattering. And it gives some information to us. The only problem is that when we say, or the experimentalists say, we have measured time, one must be very careful and understand what we are actually talking about, because to measure time in quantum mechanics is not the same, it does have the same meaning as when we say we have measured the coordinate or the moment, because we have a coordinate operator or the momentum operator, but we don't have the time operator. Again, the theorists keep working on that, and many people claim that they have produced the form that the time can be expressed as the operator conjugate to the Hamiltonian. But still this this observation made by Pauli in 1933 still makes the things difficult, because again the meaning of measuring the time is not the same. It's not related to a quantum mechanical operator. So then what is it related to? What do the experimentalists do? It is the so-called streaking technique. That's how it works. So they manage to synchronize a sub-femtosecond XUV pulse. XUV means extreme ultraviolet, so the energy is about 100 eV, and it's like several hundreds of attoseconds. They synchronize it with a longer, several femtoseconds laser pulse, and the photoelectron excited by this XUV pulse, by the bump pulse, is accelerated or decelerated by the laser field, so-called streaking field, and its spectrum shifts, the energy spectrum can be measured, and it shifts up or down depending upon what phase of the laser field the electron is, so to say, born at when it is released. And this way we can map time to energy, and what they study are the phase shift of these streaking spectrograms that can tell you the time, because the laser pulse is very well temporarily characterized, so they know at which time which phase appear. Okay, so these measurements have been routine for atoms, for isolated atoms. They are being performed since already 20 years ago. And much less studied area is the streaking photoemission of chronoscopy, attosecond chronoscopy of the solid state. So the first seminal work was in 2007, and the theory of what's going on there was suggested by Echenike. And since then, it's been used, it's been the main idea with which all the measurements are explained. So his idea is very simple, that streaking field is low frequency, so it doesn't penetrate into the solid, and the photoelectrons originate at a certain depth in the solid, which equals on average the mean free path. So the question is how much time the electron needs to reach the surface when it is excited at the approximately the depth of the mean free path. And indeed, here is the screening of the electric field in aluminum 100 surface, and indeed well below the plasma frequency, you can see the field does not penetrate into the solid. And the plasma frequency is around 15 eV, and the streaking field frequency is around 0.5 eV. So this condition is quite reasonable for simple metals. Well, then, if you develop this consideration and take into account that the probability for the electron to be detected decreases exponentially with the depth at which it is created, and then you take into account that the mean free path is actually proportional to the group velocity, and the coefficient is tau, the lifetime, which is inversely proportional to the so-called inelastic scattering rate, then you arrive at a simple formula that basically the phase shift of the streaking spectrogram is determined by this VI, which is the inelastic scattering rate, and which in quantum mechanics participates in the Hamiltonian at the imaginary part of the crystal potential. Then the famous universal curve of the energy dependence of the mean free path is irrelevant here, because everything depends only upon the inelastic scattering rate. Okay, that is correct, but what to do in the cases when the electron cannot describe the group velocity, when we are in a forbidden gap? And to answer this question, to see what happens in such a situation, we have developed a one-dimensional model which can be treated numerically exactly. So this is the model of a photoemission in a box. So the right hand side, the right half of the box is vacuum, and in the left part there is a sequence of well that simulate the crystal potential, and this is the spatially resolved or depth resolved spectral function. So here you see something like the valence band, the semi-core band, and these are the unoccupied states. And there are two forbidden gaps, simply Bragg gaps, in the spectrum. And for this system, we can solve the streaking problem completely. So we have a superposition of two light pulses, the electric field of the laser, the streaking field, and it is superimposed with the XUV high frequency field. And then what we do, we introduce a defect in the crystal, and there is a localized state formed at this defect, and then we can consider the excitation of this localized state and how it propagates, and in vacuum it is exposed to the streaking field, and then we can also consider its equation of motion, and at the same time we can construct the streaking spectrogram. And why do we need the localized state? In order to avoid this qualitative phenomenological reasoning about the mean free path. So here we know where the electron originates because we have created the defect, and this makes the things easier. Then we solve the time-dependent Schrödinger equation and analyze the spectrograms, derive the escape time from the spectrograms, and these are the two curves for the electrons originated in the second layer and in the fourth layer. And the blue curve is the instantaneously created packet, which is simply the distance to the surface divided by the group velocity. And as you can see over a wide energy region, the two curves coincide, which means that basically everything works as in the classical physics. So we can speak in terms of velocity, but close to the two gaps where the velocity is undefined, the escape times sharply drop, so it moves sort of faster. And it strongly deviates from the semi-classical prediction. So why does that happen? We will see, but in the first place, let's see when does that happen. That happens when the emission intensity drops to zero, and there may be two reasons for that. The first one I mentioned, these are the Bragg gaps, where there are no propagating states, but it does not mean that the emission is not possible there, because there are still evanescent states, which should be taken into account when we are talking about surfaces. That's why the emission is non-zero in the gaps. And the other reason is the so-called Cooper minimum, when the matrix element drops to zero. And in both cases, so for the Cooper minimum and for the gaps, we see a sharp drop of the escape time. So all the previous results were derived from the streak. And the question is whether the streaking actually works correctly for this mode. In fact, it does, because in parallel to the streaking calculations, we can derive the equation of motion in vacuum asymptotically, and then make a regression to zero, and this way to derive the escape time. And here is the comparison of the two methods for the obtained from the equation of motion and obtained from streaking, and you see they agree rather well. In the simple case, even qualitative, they quantitatively agreed, and most important is that both methods give equal information about such a counterintuitive phenomenon that the electron that originates at the first layer comes, this energy comes later than the electron that originates on the second layer. So the trajectories may be very complicated, but our main conclusion is that the streaking clock is correct. So this is quite objective. In order to understand why this happens, let us consider the temporal evolution of the energy spectrum of the photoelectron while it develops in the course of development. So these pulses show the temporal extent of the pump pulse of the exciting XUV pulse. And we consider the evolution of the spectra for two photon energies. So here you see in the middle of the excitation, the spectrum differs very strongly from its asymptotic or stationary shape at the infinite time. Whereas at this energy in the middle, it almost has the same structure as the stationary spectrum. And this happens because here in the middle of the spectrum, there is an open medium. So the presence of this very complicated, very sharp structure of the final states really affects the temporal evolution of the energy spectrum. And while the spectrum is not stationary, the electron may, or the wave packet may move with the velocity larger than the group velocity. When it becomes stationary, then the velocity of the center of gravity is just the weighted group velocity. But before that, it may be arbitrarily high. Interference effects. Okay, so all these results were obtained with the time-dependent Schrödinger equation, which, of course, we cannot apply to realistic solids because this is very complicated, very time-consuming. Fortunately, there is an alternative formalism which solves a part of the problem, the so-called one-step theory of photoemission, which is based on a simple first-order perturbation theory, and which is not capable of describing the motion of the outgoing electron, but it is capable of describing it asymptotically in the vacuum. And it is just the point where the detector is located. So asymptotically, the photoemission amplitude is just the matrix element between the initial state and so-called time-reversed lead state. LEAD stands for low energy electron diffraction. So the low energy electron diffraction is the experiment when you send an electron that is partly transmitted and partly reflected from the surface. The initial stage is the standing wave of this guy, the standing wave, and we obtain both wave functions fully ab initio with the band structure-like method based on the augmented plane wave representation. It's an all-electron method, so the quality of these calculations are supposed to be the same as the quality of the band structure that we can achieve. Okay, so this theory is well established for the stationary photoemission, and yeah, so please pay attention to this decay of the lead state, which is caused by this inelastic scattering rate and which is controlled by the optical potential. We have generalized the one-step theory to the time-dependent case, and then it turns out that the escape time that we are looking for is just the energy derivative of the space of this matrix element. So we have access to it from the same formalism, and what we obtain is just the shift of this equation of motion, because we know the slope in advance, it's a free motion, so there is no doubt about it. And the first thing to do is to compare the one-step formalism to the time-dependent Schrödinger equation, which we can do for the one-dimensional model. And so you see these two minima. The symbols are the time-dependent Schrödinger equation, and this is the Wigner phase theory. So they agree rather well, at least qualitatively. These effects of the acceleration via interference are well described. And here the results are not for the localized state, so they are for the whole valence band, which simulates the photoemission from the block state. So it's average over the whole band. And another important thing is that the dependence on the inelastic scattering rate is also described correctly by the one-step model. So now that we have established that it works, let us address a realistic magnesium O1 surface. So this is the escape time. So one of the curves, so the blue one is the average escape time from the semi-core to pi band, and the red one is from the valence band. And you see that depending on the energy, the escape time has a very rich structure, which is caused by the very complicated final structure of the final states. But qualitatively, on average, this black curve, which is just the qualitative theory that I presented in the beginning, more or less it reflects the reality. We can further compare it with the experiment, so the 4 measured points, and we are happy that the calculations do not contradict the experiment, although I cannot say that it agrees, because one needs, of course, more energy points to convincingly say that all the fine structure that we have complicated is really existing really. So yeah, this black curve is just the difference of these two curves. That's what, so the relative escape time, that's what they can measure. Okay, so let's now forget about photoemission, forget about the pump pulses and excitation, and consider pure scattering. We shall consider graphene. It's a very famous material, so everybody knows what its construction looks like. And there is one interesting point. Not the Dirac state, but the localized states above the vacuum. So below the vacuum level, the states are localized, this is clear. But also some of the states are localized above the vacuum level, and we usually explain it by saying that all the kinetic energy is absorbed by the motion along the surface, so there is not kinetic energy left to escape in the surface perpendicular direction. This is clear, but these lines further continue to the free electron continuum. And in the band structure calculations, the supercell calculations, the they are seen as special features, special lines in the spectral function. And some 10 years ago, we asked ourselves a question of what is the nature of these special lines. And our colleague, Vladimir Nazarov, constructed an analytically solvable model that proved that some of these lines are resonances. And important is that they are resonances in the mathematical sense. So these are localized states. They are eigenfunctions of the Hamiltonian, exact eigenfunctions, but for the complex energy. So this is the resonance in mathematical sense. And it turned out that these resonances are also well reproduced in an ab initio calculation, and they give rise to a very special structure in the transmission spectrum. So when we approach the energy of the resonance, the transmission probability first drops to 0, and then it steeply rises to reach unity. And in the density distribution of the lead state, so here the wave is incident from the right. The resonance manifests itself as a very sharp increase of the depth energy density distribution. Okay, so this is the transmission spectra over a single monolayer. The resonance is here. And when we increase the numbers of monolayer, at some energies, transmission resonances appear, so-called transmission slits, that with the with increasing thickness, they evolve into conducting bands of graphite. And there are two types of bands, so-called one-dimensional bands, 1D bands, where the number of resonances is simply n-1, where n is the number of the layers. They are called 1D bands because this behavior can be reproduced in a one-dimensional. But the n resonance gives rise to a different band, a band of different character. It is not split. Please pay attention to that. And that's how the scattering phase behaves. So this is the energy dependence of the scattering phase for 1, 2, etc. monolayers. The thickness of the curve is proportional to the transmission probability. So you see here in this region, for this band, the slope is negative on average, which means that there is a scattering advance rather than delay. And this is clear, small kinetic energy close to the nuclear, the electron moves faster, so it also comes faster. Whereas the same situation for that band leads to a positive slope. The band structure effects dominate here and they slow down the electron. And the negative slope in the gaps is the Hartmann effect. And indeed, so this is the Hartmann effect. The transmission time saturates and it does not depend, also in our initial calculations, does not depend upon thickness. And the transmission resonances in the 1D bands lead to very big delay maxima in the transit time spectrum. Another, okay, the N band is unsplit. like here. The interesting point is the delay on reflection. For finite slabs, the reflection delay simply mirrors the transmission delays. But in the limit of a semi-infinite crystal, limit of infinitely large thickness, of course, the transmission makes no sense, but we can still study the reflection. So in the gaps, everything is saturated and 6 layers is the same as bulk. But on reflection, in the 1D bands, there is no delay, quite surprisingly. But mathematically, this can be understood. And again, the M band behaves differently. In the limit of the infinite crystal, it acquires the fine structure. Let's now consider in more detail monolayers of graphene and boron nitride. Here, so the black curves are for graphene. We only see this one maximum due to the N resonance, whereas the boron nitride is more complicated. It gives rise to 2 more sharp structures. But in the first place, I would like to emphasize this energy at which the secondary diffracted beams appear. So below this energy, one beam comes and one beam is reflected or transmitted. And above this energy, the secondary beams that correspond to the first circle in the reciprocal lattice, they appear. And this leads to the divergence of the delay time. And this divergence is always towards plus infinity below that. But above this energy, just in the vicinity, it can be either positive or negative. And practical calculations show that for these 2 substances, it is negative and infinitely negative. So it's even faster than in the Hartmann effect. And this can be rationalized theoretically because there is a connection of the Wigner delay with the so-called dwell time, which is the integral of the density of the scattering states, and it includes the charge contained in these secondary beams. And at this energy, this charge just diverges because the K vector of the secondary beams goes to 0, and it appears here in the denominator. So that's what it looks like in the density distribution curve maps. So this is the end resonance, what I just mentioned for graphene. And in the boron nitride, it has the same shape, and also the shape of the corresponding structure in the transit time is similar, but the more complicated atomic structure of the boron nitride gives rise to these 2 resonances, which are reflected here. And the most interesting and general case is this energy at which the secondary beams emerge, and at which the transit time becomes negative. So the electron sort of moves back in time. Okay, so this brings me to simple conclusions. So if you'd like to transmit a signal, you can use a barrier, which sometimes helps. So if there is no barrier, you can ensure that the signal arrives in the due time. following the free motion. But if there is a mirror that has a structure, then there may be several scenarios. In the transmission resonances, you receive the signal with a high probability, but with a big delay. In a gap, you receive it very fast with a superluminal velocity, but with a very small probability because most of the signal is just reflected. But there are special cases when you both receive it still faster, so that even the clock moves back and without the loss of intensity. So I hope that would be useful, especially for the experimentalists, and thank you for your attention.
Questions?
Then, okay, this is the last. Then you can get signal before you pronounce or
Yes, that's true. That's exactly what can be measured. But the question is what it means to get the signal. The problem is, so that's just like the question that's been discussed in thousands of theoretical papers, that what actually happens. The problem is that in quantum mechanics, you cannot measure the wave packet twice. If you have measured it, then the wave function collapses. At least in the Copenhagen interpretation, and being very simple and primitive, because of course there are other theories that I don't understand. So the distance here between two time moments is the distance between when we know that the electron was there and we measured it. So this is the difference, to know, because where else can it be, but you did measure it and measured. And so these are completely two different aspects of life, to know that it is there and to measure that it is there. In the classical mechanics, it's the same. But in quantum mechanics, you simply cannot rely on this logic. But with these calculations that imply this negative time, I claim you can predict the arrival time. So when you have measured experiment, that's the message.
one more. Then, okay, I know about graphene, but have you shown the instruction we need for nitride? Okay, why is this so similar? This instruction or not?
From the point of view, I didn't show it, sorry. But from the point of the band structure, it's very similar to graphene, except for the splitting, that there is no Dirac state. Also, the final state of band structure looks superficially similar until you calculate the scattering spectra, and then you see very sharp resonances that are not present in graphene.
And also you have below the vacuum level the state at the K point. No?
Yes, but it is split. It's not like in graphene.
Because two atoms.
Yeah, yes.
Please.
So I'm a little bit far from this topic, but let me just try to ask a question, see if I understand something. So you say that the transmission or the way in which a signal will be transmitted depends a lot on the number of layers, for example, graphene that you have. And in this would it make any difference whether this layer have a certain, let's say, geometrical stacking, or whether you can change, for example, graphene, you can make whatever. How would it change this signal transmission, whether you have an additional structure which comes on top?
Well, according to this theory, it will change, but we cannot say in which way it will change before we calculate it. So about this negative transmission time, everything is more or less clear. So I don't know what happens, what may be the consequences of the Moiré structure. That I cannot say. But if you make a superstructure,
Yeah.
so your G vectors in the parallel direction become shorter, and then you have several. Just let me. So you have several cases like that. When the first set of the secondary beams appear, now it will with this sorry, with the superstructure, it would appear at a different energy, at a lower energy. But according to the very general formula, this should lead to another singularity. And what I can say, what I can predict, is that close to this energy from below, it would be always positive. So always a huge delay. But above this energy, I cannot say. It may be either positive or negative. So this general formula don't say that. But the superstructure, the lateral superstructure would lead to such effects. This is what follows directly from this theory. So everything depends on the actual crystal structure.
So you will have one additional feature which determines the different transmission, but it does not transmit the pattern.
It does not transmit
the pattern, because you have a pattern modulation in space, no? So you have an interface which is modulating.
The periodic structure, the lateral periodic structure, is that what you refer to as modulation?
Yeah, it's a pattern, no? So
I would simply say it's a crystal structure. Okay. I mean, for this, because I just asked this to distinguish between the crystal structure, the exact periodicity, and the Moiré structures. Okay. So I don't know what happens with the Moiré, but with the periodicity, this is clear. So the larger unit cell simply implies shorter G vectors, so the secondary beams appear earlier. That's pure geometry.
Thank you for this beautiful talk. Does anything interesting happen if your structure breaks time reversal symmetry? It is magnetic.
Time reversal symmetry. Yes, I think this might change a lot. So, but apparently you would refer then to the spin-dependent scattering, because on average, without the spin resolution, I don't see what principally may change. Yeah. But this makes, of course, the question still more complicated, because what the time is in the absence of time reversal symmetry is still more complicated. But if we keep it simple and simply consider the spin-dependent scattering, then of course you will see some effects that are not included here. That, I mean, the relativistic, the true relativistic effects.
Please.
Just since you have the slide, so from the slide it follows that when the energy approaches zero, transmission goes to one.
Yeah,
Right? So how should I concern this with general motion of quantum mechanics that extremely low energy electrons are reflected by potential barrier?
well, I think
Except there are resonances,
they are reflected at zero energy simply for the monolayer.
so this is the resonance effect.
Oh, actually, this I don't think that you can infer the asymptotics here because I don't know how close to zero I am.
Well, I mean, your points go almost to zero, right?
Almost to zero. Yes, you're right. So there it really approaches it, but frankly speaking, I don't know at which point it drops to zero if it should, because I simply didn't consider that. We can discuss it later because it's a technical issue very close to zero, say below 0.1 eV. This method is not very accurate here, and I cannot claim that it reaches unity. That it reaches unity then, that it does not drop to zero before that. So if for the system with structure, if it should drop to zero, I cannot say it offhand now. But simply, I didn't consider this asymptotics. Definitely, the curve does not start from zero. It simply cannot. The method doesn't work there.
And then another question. So you told that so when you do this toy model for the electron emission from the topmost layer, you still go with good velocity.
No.
No.
I mean, how can I?
When you estimate the weight or not. You told that this the simple transport approach works. Or not?
Sorry, what I
So that was a picture of the emission from the first layer.
for the first layer, for the toy layer, but there yeah, I know, I see what you mean. I said that it was just let me see, what was it? So here I compare the instantaneous mode for the fourth layer, right? And for the first layer, I don't do that. What I do here, these two curves, one curve is inferred from streaking. Yeah, the other curve, I switch off streaking and I just watch the equation of motion in vacuum. And then this is regression. So no, this is only for the fourth layer. This here, you're right, it's meaningless. But I mean, it would yield like zero time, right? Zero time. But instead of zero time, you have structure. That's the message.
No more questions. Please.
So you said that only inelastic scattering reduces the mean-free path.
Yes, this is our simple assumption that mean-free path is due to the inelastic scattering, because that's the only thing that is not included in our band structure.
But in principle, any scattering, elastic also.
Here we refer to inelastic scattering as everything that washes the electrons out of the channel that you observe. Yes, it can be also elastic in the sense that this stray scattering. Yeah, all this is under the notion of an elastic scattering. It's phenomenological. We call it electron absorption.
No more question. Let us thank speaker again.
You did not understand everything. Yeah, it was like too many to.
I mean, I'm very far in that, and so that it's not always. There are a lot of assumptions, I think, and a lot of knowledge in the basis of what you're saying.
It's a long story. It's like many decades, of course.
But so and then I thought this answer that you gave to the question of information transmission, I thought, okay, it's you can tunnel, but with a very low probability. So I'm thinking information in the sense I'm applying this laser pulse and the signal comes out, or I'm not applying it, no signal comes out. So that should be a bit. This bit, can it ever arrive earlier than I said?
In this sense, of course not, because if you change something on one end, you cannot expect the changes to come earlier to the other. This is, this also was, of course, one of the arguments to reconcile, which is already present in the literature. So you are right that it is not sufficient to send one particle. You should send like something like more than
right, exactly. That, I mean, that what you produce. So for a true message, you would do this.
So something on the left hand side should change. And that's.
And then when you do this, so if you measure with respect to the time that the sender sort of decides to send a message, then the delay will always be positive.
Exactly.
And depend on the distance somehow between. So if you make your intermediate layer thicker and thicker, also this time.
Yes, this is clear. Although one can.
It should be clear, but these papers on transmitting Beethoven's symphony faster than light, they were, at least to me, claiming something different. They were somehow, as I understood it, seeing this in this evanescent wave, and then claiming, okay, I detected it earlier than I said it. Well, I detected it 10 times faster than the speed of light. There were these experiments, I suppose you were referring to.
So then not to this one. I know that
when you talk about it, talk about it in polite form.
I mean, when you define all the notions very clearly, very relaxed, then all these like things disappear.
Right. This is what I like. What I kind of would expect, and then so maybe if I may this delay